So I'm going to spend the next 25 minutes having some fun with you guys. Since you stuck around, you get to see some details about what we're doing in R&D that not everybody will get to see. Just make sure you don't tell the colleagues that left before today. It was really fun to watch Jonas go back to see where PacBio's been and going from one ZMW over the years to tens of thousands of ZMWs to millions of ZMWs. But what I will say is over the last 4 years, it's not been just around the sequencing technology. And yes, we've moved onto some more advanced sequencing technologies, but it has been the workflow around that. Whether we're partnering into that workflow, acquiring into that workflow, or just building that out. You know, as you've heard, it's not that easy to always get great high molecular weight DNA onto the sequencer easily. That's going to work every time. And it's not easy to analyze that data on the back end as well. And so a lot of effort around not just building the sequencers. That being said, building the sequencers is really important for us. And so I'm going to spend most of my time today talking about the long read portfolio and the sequencers and the work that we're doing in R&D there. Now, unfortunately, over the last few weeks, we've had to do some restructuring of the organization, as I'm sure you guys are aware of. I don't want that to concern you. You know, we're doing that to make sure that we're healthy and viable and focused on the right things. And I actually think the narrowed focus on the left half of this, so on the long read portfolio for the next 18 months, is going to be a really important thing for the company and for my R&D organization. You know, we are going to continue to make improvements on Vega, so look for us to be looking at how we get that low sample input from the SPRQ chemistry onto Vega this year. We're going to continue to push the envelope on Revio. It's really important that we continue to make advancements there to give you, further capabilities with that and advancements in the technology. I'll touch on some of that. I'm mostly going to focus, though, on what does really high throughput sequencing look like for PacBio. And I say that we can start to focus on this now, and it's a priority because of the work that you guys have done. Revio has helped people do HiFi at scale. Dave showed that, in the last 18 months, we've generated more HiFi data than we had in the entire history of PacBio. That's an important thing because people are starting to understand what they look at when they see our data. And more people around the world are now getting access to that with Vega. And so for us to start thinking about a sequencer that can do tens of thousands of genomes, and I use genomes as an equivalent just to frame sort of the scale, knowing that not everybody's doing genomes. If something that can do tens of thousands of genomes a year at $200 a genome or less. And so that's really the framework that we think about is how do we make sure that we can get HiFi into that type of an application setting so that when you guys have a choice of what your experiment should use for a technology, it's no longer just about the price or the simplicity of the workflow. It really is what technology is going to be the best one for me to use. Now, Christian put this slide up at JP Morgan, and we immediately started getting a bunch of questions. Now, at first I want to just frame it with, JP Morgan isn't a customer event, it's not an industry conference, it's an investor event. And so when we put these things up, a lot of that is just showing the investors that yes, we do have a roadmap, we're not done with Revio, we do think that we can drive profitability in the business. And so you hear things like gross margin and things that you don't care about. When I think about this, it really is, how do we reduce costs? And how do we get higher throughput to enable the scientific community to use our technologies? I will dig into that. But Christian, we can't always script him. He did say at JP Morgan, and the last half of this sentence is probably what matters, is, the goal now is the ultimate goal of achieving cost parity with short reads. So forget about the gross margins, that's how we get you to cost parity. But he put this out there in January with intent. We showed the slide, we want to be able to show that we can get there. And so I want to go and spend some time on this with you guys today to give you the confidence that when Christian said that and we showed this, that we actually have these technologies in R&D ready to come together. And for the first time, we do believe that the markets are ready. We're getting pulled into more and more of these discussions around 10,000, 20,000, 100,000, 1 million samples. These projects are out there. Dale even talked about, at Myriad, with targeted panels, how do we do thousands of samples a day? Right? There's the scale of what we need to go and do this. So I'm going to start, and I know that not all of you are engineers. I'm not an engineer either, but I've got some brilliant engineers at PacBio that have been developing our smart cells over the years. I'm going to start with the semiconductors. So moving from a 200 millimeter to a 300 millimeter fabrication is an important thing for us. Now, for those of you that don't know the metric system as well, that's like 8 inches going to 12 inches in diameter. Most of the industry has moved to 300 millimeter fabrications around the world. That's where most of this is being made. I promise you Apple is not still on the 200 millimeter lines, but we are. And so that industry has leapt forward in the last several years, and we are now taking advantage of these new advancements. If you just think about pure size of the wafer, if we were going to just continue to do our 25M chip on these wafers, we could punch out at least twice as many chips. So think about that as an immediate ability to reduce costs of our 25M chip just by moving to these newer fabrication lines. But over the years, the features you can build into these have improved. And so not only can you get more chips out of these, we can think about how we further shrink the feature sizes to take advantage of some of these new technologies. The hardest thing for us to go from the 8M chip to the 25M chip was what we refer to internally as crosstalk. So what's the noise coming from all those neighboring ZMWs? And what's the impact of that when you start crunching all those ZMWs closer and closer together? And so the hardest thing to get the 25M chip was reducing that crosstalk, which is why we partnered eventually with Google to come up with the deep consensus algorithms, where they really were removing that last 10% of that crosstalk because the pixels were so much closer together, or ZMWs were so much closer together. But these new technologies now let us crunch those together and reduce that crosstalk. And so not only will we be able to get more chips, but we can get more ZMWs on each of those chips, which again is effectively going to drive down the cost of those chips. Happy to say we do have these chips in-house. They are slightly larger than your 25M chip, but the physical area isn't dramatically different, but we've squeezed a whole bunch more ZMWs onto each of those surfaces of those chips. And we've been sequencing with those. And so what we wanted to immediately look at is, what is that crosstalk going to look like? Is this going to be something that we can work with and scale with and really start to drive into a technology? So there's a few different comparisons here of Revio runs to runs now on this new smart cell that we're using. And you can see that the yields, if you look at an equivalent, so we're just looking at an equivalent 25 million of those ZMWs across Revio in this new chip. We're trying to make them apples to apples when we do these studies. You can see that the yields of HiFi look really good. The conversion, there's not just the loading on the chip, there's the conversion of those into a HiFi read. The conversion of these to HiFi reads looks really good on these new chips, and the overall accuracy. So we're getting even a little bit better raw base accuracy, which means that we're having a little bit better HiFi Q30 read on the end. So the chips are in-house, sequencing beautifully. We're really excited on what we're going to be able to do with these on next versions of technologies. Next, I want to talk about the chemistry. So the beauty of being at PacBio is we work with brilliant engineers, but the surface chemists, the enzymologists, the people that get the biochemistry to work on a semiconductor are some of the most talented people that I've seen in the industry. And so what we've been able to do with you guys with Revio is introduce this SPRQ chemistry, which is the red on the top. And even since launching the SPRQ, and some of you are still just starting to use that, we've been looking at different ways to stabilize that chemistry even further. And on the left, you see some curves. It reminds me of how amazing this is. We're watching a polymerase in every one of those ZMWs add a base at a time. And we're measuring there, and what I'm plotting is all 25 million ZMWs, or all the active ZMWs, and how long it's taking the polymerase population to add a base. And you can see that the top graph is a little bit broader, which means that there's some of those wells, the polymerase is going a little bit slower than the others, and now we're starting to narrow that in. Our polymerases, we like to go just over 2 bases a second. A wild-type polymerase would add hundreds to 1,000 bases a second. So we've slowed our polymerase down that much to be able to monitor and measure the activity of when it incorporates the next base. And so what we've been able to do now is we've been able to make a tighter peak just around 2 bases a second, which means that these polymerases are a lot happier on a general population, and you'll see the impact on that. You see that it's already improving the insertion errors. If we have some small issues, we're obviously great as you get more passes, but you can see here, the insertion errors are coming down with these formulations. Deletions relatively unchanged, and mismatches are always a really, really simple thing for our polymerases. But more importantly, what these new formulations are doing is they're helping with this HiFi conversion. And so because now we've got a more consistent population of polymerase at that just over 2 bases a second, you can see that now with equal loading, you're starting to see, again, further yields of HiFi. So more of those ZMWs are actively turning into the HiFi population, which then gives us better quality and, again, increases in yield. So we're continuing to push this SPRQ chemistry for both Revio as well as for future technologies with the new chips. And this really gives us an option where we can start to think about the trade space that we want to work in. How fast do we want our polymerases to go? What frame rates are we going to build into our semiconductors? Because maybe slower is not always better. Maybe a faster frame rate and a way faster polymerase is a better way to get accuracy. And it's all this trade-off to get to the yield and the quality of the experiments that we're doing. So the chemistry team is on a real roll. We also want to talk about multi-use chips. Now, you're probably like, why would you care? The chip is the most expensive component of what we ship you. So when you order your $1,000 Revio kit, or your Revio smart cell, that smart cell is the majority of the cost of that kit. It's not the polymerases and the dyes. They're expensive, but it really is the chip. And so if we really want to get to price parity with short reads, we probably shouldn't throw away that chip every time we use it. And so what we've been working on is how do we think about multi-use of that chip so that you can, in this example, rather than just add library per chip, maybe you put add library on and you run it 4 times across that chip. And you want really high depth of things. Or you've got a lot of samples in that library. Or maybe in another example, I don't want to get that many reads for that library. I'd rather run a different library every time on that chip. And so we're working to be able to enable those different options for how you're going to use these chips in our systems. Now, when we first did this proof of concept, we said, okay, so let's put, on the first use, let's put a human sample, and then internally we use a lot of this 11 KB sort of library. It's just sort of a control library for us. So let's put those and load them and strip them off and then switch them so that if it had the human sample the first time, it's got this 11 KB sample the second time, and does it still load? And do you get crossover? And fortunately for us, we didn't see the carryover, and so the stripping of that first library out of the ZMWs is working extremely well. And we were able to load those chips a second time. So then we started to push it. And on the top, we said, okay, well, what if we don't just reuse it once, but what if we multi-use? What if we use it a third and a fourth time? What starts to happen? And on the top, you start to see there, this is just looking at the loading efficiency. And so that P1 plus P2 is what percentage of the ZMWs have 1 or 2 polymerases loaded in them. And you can see that really started to tail off on us. So like, okay, maybe it is just one-use chip, but we'll still take that if we can. But then our surface chemists took over and started to really understand what's happening on that surface, what's preventing the loading on those second, third, fourth, why are we starting to lose some of the efficiency? And you can see there on the bottom, rather than dropping off, we're getting those loading efficiencies for the second, third, and fourth use close to 50% P1, P2, which is really encouraging for these early studies on multi-use chips. And so it's great to load, but what happens when you actually start doing the sequencing on these chips? And so plotted here are a number of chips used 4 times each. The first one on the left, you see, loads best the first time, converts into the HiFi yield. That line up top is, I think, 100 gigabases. Yeah, so something over 100 gigabases of yield on the first use. The second, third, and fourth uses, I just showed you, the loading's not as efficient, but look at the yield on HiFi. The polymerases are really happy in those ZMWs, the second, third, and fourth uses. So we're getting that nice peak that I showed you with that chemistry change, where you really have a really great population of polymerases going just over 2 bases a second. So the conversion to HiFi is almost as good on those second, third, and fourth uses as it was on the first use. So we're really encouraged by that. On the right, it's showing on those chips how much yield of data we got off them. So 3 of those chips over the course of those 4 runs gave us 500 gigabases of yield. One of them, the lid popped off and it leaked on the 4th use. And so we have some adhesion issues that we have to fix, and some of you might have had a leaky chip or 2 over the last month. This time we did too. So you might say, why do I care? Like, why do I care if you can get 400 or 500 gigabases off of one chip? Well, you care because it inverts the economics. So now the chip is no longer the most expensive part of the run. By the 3rd and 4th run, you're really buying the polymerases and the nucleotides from us, and the wash buffers. And so it inverts the whole economics so that we can really dramatically drive down the cost of the sequencing on Revio, Vega, or future technologies. So really exciting work that we're doing with the chip reuse. What I can't ignore is the back end. And so we've made huge advancements in how we think about building out the computational biology team to support the different pipelines and the different types of workflows that you guys are doing. Earlier this year, we had our commercial meeting, so we did a kickoff with our sales team. And I was having some fun with it because I don't know if any of you have teenage daughters. They speak a totally different language. there's this teenage slang, and maybe it's a California thing, but I played a video of my just turned 15-year-old daughter, and she says things like, PacBio is low-key, the best, no cap, Illumina and Oxford Nanopore, sus and mid, HiFi's, she'll say HiFi is Sigma, stand on business mark, it's a whole different thing. And I had to take time to learn, what the hell is she saying to me? And I feel like that's where we're at. We're trying to teach people what a genome is, not just a high-confidence genome. We're trying to teach them about transcriptomics and isoforms, not gene expression. We're teaching them about epigenomics and use of base resolution for epigenomics and not your CPG arrays. And so I feel like there's this whole new language that we're trying to learn, and I'm asking all of you to keep perpetuating that language. But we do have to shift, multi-omic analysis, all the variant types, all of the sequence, consolidation of testing. And so it's a real challenge that we're at. And I just want you to know that we are working really hard on helping people understand the language that our sequencers are providing to the scientific community. This is just an example of, for human whole genome, our workflow. If you haven't been using this pipeline, pretty simple WIDL pipelines now. You can access these. There's some cloud-enabled partners that can provide these to you. Everything from the SNPs and indels through the different structural variation, the tandem repeats, segmental duplications. A lot of these are built as well for targeted panels, not just the whole genome, but can be used for both. A really comprehensive tool that we're continuing to advance and make a lot of progress. It's becoming much more standard for HiFi genome analysis in the clinics right now, and I expect in the research community as well. We've also recently partnered with Dennis Loh at Chinese University of Hong Kong, and I don't know if you saw his publication that came out last month. He's made some further advancements on our ability to look at epigenetic markers. Improvements to 5-methyl-C. You can see in the middle there his improvements on his first version of HK1 versus his HK2. Our performance is more like HK1 currently with Spark than it is HK2. So expect further improvements on 5-methyl-C. He's made improvements for 6-methyl-A. Right now we're using it mostly for the fiber-seq application, but there are a lot of other organisms that have 6-methyl-A naturally occurring in there, and so start to open up more of that prokaryotic community for 6-methyl-A calling, as well as he's been able to train it to the 5-HMC intermediate out of the 5MC signal, which is a big advantage for a lot of different neurological and some of the different cancer applications that people are doing. So great to see that. Expect that coming out later on this year, early next year as well. We're in the process of retraining all those now with the Spark chemistry. Now, you've heard it a couple times, not everything should be a whole genome sequence. And I loved how Dale presented that this morning. He's got very specific targeted genes or gene regions that he wants to look at, and he has to do lots and lots of samples. And so targeted panels are never going to go away. It's been a real focus of ours. We no longer think that it's just going to be a genome, and so the investment in targeted approaches and the partnership into this across these different areas, so the carrier screening, some of the repeat expansions, pharmacogenomics, you saw some HLA work this morning, some of even the long-read low-pass are really important applications of HiFi sequencing. And we're going to continue to partner and build those out and expand them. And for those of you that went to Sarah's workshop yesterday, we are also this year going to be doing some advancements in our pure target applications, driving that cost down. This has to be less than $100. For many of these applications at scale. Dale was talking about he needs to get more samples on Revio, so we're going to be increasing. Now with the Spark chemistry, we get better coverage. We're increasing from 48 samples per smart cell to 96 samples per smart cell, and with the automation in and around that. We are also expanding that content, and so for the current pure target, we've made some advancements in the target caller on the back end, so expect a repeat expansion 2.0 coming out of us, as well as then expanded content for carrier screening. Much like what Dale was showing, there's a subset of genes there that are very common. There's a subset that are really, really hard to look at, and so look for us to put together a comprehensive targeted carrier screening panel for you guys to go and explore with the pure target application. And then custom. It's really hard to get a perfect panel for everybody. Everyone's got their favorite gene, their favorite population, maybe they're just a different ethnic group with different carrier frequencies. And so the ability to customize the pure target will also be rolling out later on this year. So I want to come back to this because I think it's really important that you guys understand where we're taking our technologies. It's also really important that we address throughput and cost. Years ago, it was long reads are long, expensive, and dirty. We cleaned them up with HiFi. It was a huge effort with the HiFi sequencing to make sure that our reads were long and accurate. And I argue that they are the most accurate reads now, and probably because of the uniformity of coverage. But for some applications, it's still not high enough throughput with Revio or cheap enough. And so we're putting these technologies together with a primary focus, with all of my R&D organization focused on long read portfolio right now, so that we can continue to enable you guys at the price points and give you guys the choice of the technologies that's not just financially driven. With that, I'm going to stop, and I'll say thank you for attending. It's been wonderful to be with all of you, and I look forward to see you all soon. Thank you.